In this video, we will practice some vector and projections questions. First, take a moment to review what we learned in the previous 3 videos. Let's start with question 1, which asks to find the cross product between vector b and a. First, let's create the 3x3 matrix. Next, we need to find the determinant. So let's use the method of cofactors. First, we're going to cross out the rows and columns with I, then write out the 2x2 matrix left behind, and multiply it by I. Next, we need to subtract by the 2x2 matrix times j, then add by the 2x2 matrix times k. Then to calculate the 2x2 matrix, we first multiply the first diagonal, then subtract by the second diagonal, like this. After we do that, for the rest of the 2x2 matrices, we get this. Then after we simplify, we get this vector, -5, 5, -5. In this question, we're given some vectors and need to simplify the expression. This question is purely computational and we just need to make sure we do everything correct. You can pause and try it on your own. The answer will appear soon. In this question, we want to find the values of c that will make the vector a unit vector. Recall that to be a unit vector, the vector just has to have a magnitude of 1. So let's call this vector v and write out the equation of its magnitude. Then let's set it equal to 1. And after we solve for c, we actually get 2 values of c and both of them would be valid. Let's see why there are 2 possible values of c. Since the c is in the z component, the vector will go up and down. Notice that the length of the vectors change when they go up or down. We can also see how there can be 2 possible values of c that make the length 1. In this question, it's asking for a vector that is 30 degrees with I and 60 degrees with j. First, let's graph the vectors I and j. I would be the vector 1, 0, and j would be the vector 0, 1. Let's draw the vectors that are 30 degrees with I. We can also see that only one of them is 60 degrees with the j vector. Based on that, we can say the second condition is not redundant. Otherwise, there would be 2 answers. To find the components of that vector, we can create a right triangle with the hypotenuse 1 and angle 30 degrees. Then we can take the cosine and sine of 30 degrees to find the x and y values. After we find the x and y, the vector would be as shown. In this question, we want to find the scalar projection of a force onto the vector 4, 1. First, recall the scalar projection formula. Here, vector A would be the force vector, and vector B would be the onto vector, which is 4, 1. Vector A will have a magnitude of 50 in the direction 1, 4. To get that vector, first we have to get the unit vector, then multiply it by 50. So first we get the unit vector of the direction, then we multiply by 50, and this will give us the force vector. We will also need the magnitude of B, and that would be square root of 17. Now we could put this all back into the equation. In the numerator, we have a scalar times a vector, dot product with another vector. According to the shown property, we can take the dot product first. When we do that, we get this, and this is around 23.53 newtons in the 4-1 direction. In part B of question 5, they're asking for the work done from 0, 0 to 4, 1 from the previous force. So let's graph what we have. This green vector is the force vector of 50 newtons in the 1, 4 direction. The red vector is the distance vector from 0, 0 to 4, 1. To get the work, we have to find the projection of the force onto the distance vector. Then we can multiply by the distance. We already found the projection of the force, which was 23.53. We'll label that FD. Then we need to multiply by the distance, which would be the length of the distance vector. When we do that, we get around 97. On a side note, we could have just taken the dot product to get this answer too. I'll explain this in the next slide. Let's look at the scalar projection. Then let's solve for the dot product. And let's look at this graphically. The projection of A onto B would be this length here, and the dot product would be this length times the length of the vector B. Let's also look at the projection of B onto A. And when we solve for the dot product, this is what we get. And graphically, that would look like this component times the length of A. So this is a new perspective to the dot product in terms of the scalar projections. And we can use this to solve problems like the previous problem. In the next video, we will go over lines and planes in 3D coordinates.